Welcome to the video for superlab Iod503, interpolate between data points in a table or graph. As we get started for today, you should make sure that if you're watching the video, you have the skill sheet in front of you so you can follow along with us. If the video says pause, you should pause, and you can work on your own. We're going to get started by reading the background information, which is at the top of the skill sheet. The background information will tell us what we're actually doing when we interpolate. This is an important place to start. So we have a volunteer to read the background information for us. Hey.
On interpolate skill, Iod503 asks you to estimate the data that exists between other known data points. You can try to look between two given points on a graph, or you can also interpolate the data from the table.
Excellent. So when we say interpolate, we're looking for a middle number. Often this middle number doesn't actually exist. We kind of have to estimate what would be between two other numbers. So in order to take a look at a sample of this, we see this table. First listed on the top, we see for two different years, 1900 and 2000, what the average temperature was in degrees Fahrenheit for a few months. So what the question is asking is, what is the average monthly temperature in April of 1900? So how would we get this answer? How would we find the average monthly temperature in April of 1900? Do you have an idea of how we would answer this problem? What do you think?
March 30,
Excellent. So if you look, we're looking for the average monthly temperature, which is given to us on all these numbers. Now, we don't know if we're looking for 2000 or 1900 until we read the question carefully. Since we're only looking for 1900, we only care about this row right here. Where do we care about this row? Well, we're looking for April. Now, where would April be? It's between which two months? March. Excellent. So the April data is not actually listed, but we know in reality April would exist right here in between March and May. So what we need to do is take a look at the March number and the May number and find the middle-ish number. All right, we're looking for the number in the middle. Now, if you're doing this as accurately as possible, what you would do is add them up and divide by 2 to find the average. However, in this case, on the ACT, you're not going to have a calculator with you, so you're going to want to start getting the hang of picking a middle-ish number. All right, the way the ACT is set up is they'll probably give you answers that are somewhere around 40, let's say 52, 63, or 78 would be your 4 answer choices. And so what you'll see, while 52 is the correct answer, the only thing we want to be careful of is technically 40 is between our two numbers, but it is way too close to this side in order to actually be the middle number that will be between. All right, so you just want to be careful with some questions like that. All right, so let's take a look at the passage that's actually for this skill sheet. Passage 3, talking about chemists and the experiments they performed. We have a volunteer to read the introduction sentence for this passage. Now, as our reader is reading, as we've always done, if you've ever watched any videos before, what you're looking for is to circle or underline or highlight or mark in some way, shape, or form any words that are tricky or confusing to you, so you don't let vocabulary get in our way. So everybody should have some sort of writing implement in their hand as they're going through this, so that you can circle, highlight, or underline any word that our volunteer reads for us in the introductory paragraph. All right, so now that everybody has their tools in their hands and are ready to go, we should get started.
Chemists performed 3 experiments to determine the boiling point. 3 points are purified water, H2O, solution of various types of solids dissolved in H2O.
All right. So did anyone have any words that jumped out at them that they were unfamiliar with in this that we should define together in circle?
Purified.
Purified. Nice. Any other words that jump out? Solids. Nice. Any other words? All right, so if you remember, there's always 3 ways that we can figure out the definitions of terms on an ACT. It's either defined for us in the passage, which is convenient, but it doesn't have to in this case. Or we can use background information or context clues, or we can always look it up in a dictionary. In the actual ACT, we can't do that, so we're going to try to use background knowledge or context. Now, when we say purified water, does anyone have an idea from background knowledge or context clues what we mean by the term purified?
Clean water.
Yeah, it's clean, and it's removed of everything, not just necessarily bacteria, which you would use if you were trying to purify water yourself, but it also has any other contaminants that's been added to it removed. So like water in Chicago, does anyone know what water in Chicago has added to it that's more than just water? there's usually two things that are added to the water in Chicago. You know one of them?
Salt.
Thankfully, there's no salt added. That would be very funny tasting water.
I heard it was like a bleach like that.
It's chlorine, yeah. So it's essentially low amounts of chlorine that are used to kill any bacteria that are in the water. And then there's also fluoride that's added to the water. So it's stuff that makes your teeth stronger. So every time you drink Chicago City water, you're actually slightly improving your teeth. All right. The problem with that is if you use this in an experiment like we're talking about, you wouldn't have just water. You'd have water with chlorine in it and water with fluoride in it. So purified water has all that stuff removed from it. All right. And then solids, when we talk about solid, it's just any sort of solid substance. So in this case, like the shaker of salt that you have on your kitchen table, that's solid salt on the inside, and that's the solid content. Let's take a look at experiment 1. We have a volunteer to read experiment 1 for us.
50 milliliters of H2O was heated in a beaker. The temperature of the H2O was recorded every 2 minutes until it remained constant, indicating the boiling point. The procedure was repeated with a solution of 5 grams of sodium chloride and 50 milliliters of H2O and 10 grams of NaCl and 50 milliliters of H2O. Results are shown in figure 1.
Excellent. Are there any terms in here that we want to make sure to clarify and go through? No? Everybody was good with the oil? Chloride. Nice. Good. Any other terms? Great. Using background knowledge, does anyone have any idea if substance is called chloride, what does it probably have in it? You have to use some background knowledge of chemistry. Chlorine. Fantastic. It's any molecule that has chlorine in it. If you write out the actual name of it, sodium chloride, it's just if you take sodium and stick it together with a chlorine, you get sodium chloride. You'll notice later on in one of the passages we actually talk about down at the bottom potassium chloride, and that's just potassium stuck to a chlorine, and calcium chloride, which is just calcium stuck to chlorine because of its valence shell, if you remember all the way back to chemistry, in order to even out the 8 electrons in the outer shell. All right, so let's move on to experiment. Actually, let's take a look at this experiment one more time and just investigate what they actually do here. All right, in this experiment, we had scientists who were doing an experiment. What was the experiment that they were running here?
They were measuring the boiling point of water.
Excellent. They're measuring the boiling point of water. How are they measuring the boiling point of water? Like, how did they actually do it in this experiment? I'm sorry, say one more time. Yeah, how was it measured? So they took a beaker that was full of water, and what did they do with the beaker full of water? Heated it up. And then what did they do with the water in the beaker as it was being heated?
They recorded the temperature every 2 minutes.
Good. They recorded the temperature every 2 minutes. And they kept doing this until what happened? They saw something happen after a while. Like that water. They did what? Yeah, the temperature remained constant. As soon as the temperature remained constant, what did that tell the scientists that they had reached about that liquid?
That it was purified.
Oh, so that's a good point. The water was actually purified before it was started, or else we would get false data.
The boiling point.
Yeah, so when the temperature levels out and it stops going up, that's how we know it's the boiling point. So if we take a look at the graph that they made this graph. Starting with pure water, which is the solid black line. And so we have our time here on the bottom. They took a temperature reading every 2 minutes. And we see the temperature on this side. As the time went by, you'll notice that the lines get higher and higher, because the more you heat the water, the hotter it'll get. And it'll keep getting hotter and hotter and hotter until eventually you notice that all the lines level out. And what does it mean when they leveled out? What did they reach?
The boiling point.
The boiling point. And that's how you find the boiling point of a substance. You just keep letting it go and go and go until the temperature finally stops going up. So when water turns from a liquid into a gas, when it boils, it actually won't get any hotter. That energy is used to change the molecules from a liquid to a gas. Right, so the temperature will actually remain constant. All right, now they did this for pure water. Then they also did this a couple other times, except for the other times were a little bit different. They did this 2 other times. What was different about the other times?
The other time they use sodium chloride.
Excellent. And how much did they use?
They use 10 grams of it.
They used 10 grams one time, and then how much the other time?
And then the next time it was 5 grams.
5 grams, right. All right, so they ended up doing it 3 times. They used 10 grams of salt, 5 grams of salt, and the first time what you have to remember is they used 0 grams of salt. All right, 0 grams of salt would be no salt. And it's going to be important to remember that this line right here actually is H2O plus 0 grams of NaCl. They didn't actually add any salt to it there. All right, so when we start to interpolate later, we do need to remember that essentially this number would be 0 because there's nothing there. Okay, let's take a look at the next experiment, experiment 2. We have a volunteer to read experiment 2 for us?
The beaker containing 50 milliliters of H2O was placed in a dry an insulated bowl of solid CO2 which produced temperature below 70 degrees Celsius. When the H2O began to solidify, the temperature was recorded. The procedure was repeated with various amounts of NaCl added to 50 milliliters of H2O. The percentage of NaCl by mass, the mass of NaCl, and the freezing point are shown in figure.
Excellent. All right, from that reading, does anybody have any vocab words that jumped out that we want to make sure we clarify?
Insulated.
Insulated, nice one. Other words? No other word in here? Solidify, nice. Here, solidify. Good. And any other ones? All right, so if we take a look at these 2 words, does anyone use, so we don't have insulated defined for us in the passage. Did anyone ever had any context clues or history with the word insulated? Yeah, so it's usually part of something. And what does it mean to be like an insulated container? It's like maybe you actually have containers that are insulated before. What does it mean to be insulated?
Well, I know that usually houses are insulated.
Yeah, so you put insulation in your house. Why do you put insulation in your house?
Keep the temperature, if you're
Yeah, perfect. It's to keep the temperature either hot in the winter or cold in the summer. All right, it acts like a barrier that prevents heat from going back and forth. So your house is usually insulated. So if you were to like take a look at your walls, and you ever opened up your walls before, there's usually either pink stuff inside of your walls, like pink foamy kind of stuff, or there's sometimes it's white. Sometimes it's actually like a spray-on foam that's in there that's insulating the walls. Essentially what it's doing is it keeps the heat wherever you want it to be. So if this is the inside of your house and you want it to be hot, it keeps the hot air in and it keeps the cold air outside so that in the winter you don't lose a lot of heat from the inside of your house to the outside because you just be wasting heat that way. So the better insulated your house is, the more it stays the temperature that you want it to stay. All right, so in this case the bowl is insulated, so it just makes sure that the bowl is not transferring a lot of that cold from the dry ice out. And then solidify. What do we mean by solidify? What word do we see in there? We see like a root word in there. Solid. Solid. And so whenever you add the IFY, it's just to make something more like that. So if you solidify something, you just make it a solid. Okay. So then taking a look at this experiment a little different than the other one. What did they do in this experiment? They weren't measuring boiling points. What did they do instead? Right, they took water, just like we had in our other one, but they did something with it. Yeah, what did they do with it?
Tested the freezing point.
Yeah, in this case, they're looking at freezing point. So instead of heating up a beaker, what did they do with that beaker of water? Yeah, they froze it. How'd they freeze it?
They placed it in dry ice bath.
Nice. Have you ever seen dry ice before? It's the stuff in like the ice cream carts. All right, it's like a block of actually frozen carbon dioxide. If you were to touch it, you get really bad frostbite. It's really, really cold on it, but it's the stuff they keep in like ice cream carts in order to keep the temperature really low. All right, so they were chilling out the water using dry ice. All right, what did they then do starting here? So they did it with pure water initially, and then what did they start to do with the water that they were chilling? With what? Yeah, with different amounts of NaCl. All right, with different amounts of salt. NaCl is like table salt you put on your food. All right, so they kept adding more and more and more, and eventually what you get is a table that looks like this at the top here. All right, you see how much salt was added in percentage, how much what the mass of salt was, and then what the eventual freezing point that they measured that to be was. All right, they then did this again according to experiment 3. They then did this again in experiment 3. How did they do this in experiment 3? Yeah, go ahead. You want to read experiment 3 for us?
The freezing point of various solutions of potassium chloride and calcium chloride were measured using the same method as in experiment 2. The results are shown in table 2 and 3.
Nice. So instead of using salt, what did they use in this case?
Potassium chloride
And which other one?
and calcium chloride.
Nice. So they did the same thing, and that's how you get the data that's listed here. Potassium chloride and calcium chloride. All right, let's do some interpolation. If we take a look at an example problem with look for interpolation, it says according to figure 1, what was the temperature of the water with no NaCl added after 5 minutes? All right, now this is actually not an interpolation question. This is just getting you to be able to use this graph effectively. So if you were to see this question, how would you answer this question? All right, if you were to see this question according to figure 1, what was the temperature of the water with no NaCl added after 5 minutes? How would you answer this question?
Grab between 4 and 6.
All right, you go between 4 and 6 degrees or 4 and 6 minutes. All right, between 4 and 6.
And then you go all the way up to the water with no NaCl for that.
Then which line is that?
That is the line, it's like a charge for that line.
Yeah, good, the solid one. All right, then what happens? Then what do you do? Now we hit that line.
Crossover.
Yeah, cross over. All right, now depending on where you hit it, you notice that the answer that's actually given here is 78 degrees, but what we found is it was, I don't know, more like 76. Again, on an ACT, when you have to estimate numbers like this, they're never going to give you, was it 77, 78, or 76. They won't give you numbers that are that close. Instead, what they'll do is they'll actually try to trick you with some of the numbers. What they'll do is they'll either start at and hit the line right here, so hit this dash line, the one that has 10 grams of salt instead, and they'll give you this as a possible answer. So they'll say like 60 is one of your answer choices, or they'll say then 66 is one of your answer choices, which would have been a 5-gram line. So those are the kind of answers that they'll give you as possibilities. They won't try to make it really specific and say 76, 77. All right, here's what you want to do right now. You want to answer questions 1, 2, and then 3, and 4. All right, when you've answered questions 1, 2, 3, and 4, you can certainly feel free to use the hints if you need to. All right, but when you've answered the questions, you feel like you're ready to take the, go through the answers together, you should press play. As right now, you should press pause so that you can answer them on your own. Again, when you're ready to take a look at the answers, you should press play. All right, if you are pressing play at this point, that means you've already answered questions 1, 2, 3, and 4. You're ready to go through the answers to make sure you got it. Let's start with question 1. According to table 1, what would be the freezing point of a solution with 1.5% NaCl? What'd you get for your answer here? Negative 1.8? Negative 1.8 bananas? Good, degrees Celsius. So we're looking for a freezing point. Our units of freezing points are in degrees Celsius, and we need to make sure we have degrees Celsius. All right, now, how did you get this answer? You got 1.5% NaCl. Okay? Okay, we're looking somewhere between 0 and 3. So if we're looking between these, we draw a line over. What's the freezing point? Now be careful, the only thing is though, negative 1.85 is the freezing point if it were 3%. So you know what it is at 3%, which is negative 1.85. You also know what it is with 0%. And you want to go in the middle to get to 1.5. So what would be the answer here if you were in the middle? What's kind of in between 0 and 1.85? A little bit more. What if I said 18 instead of 1.8? What's half of 18? 9. So half of 18 is 9. Half of 1.8 is point. Yeah, so half of 18 is 9. So half of 1.8, we just move our decimal point over one spot, would be point. Negative 0.9. Okay, so somewhere around 0.9 or negative 0.9 degrees Celsius should be our answer. All right, now again, if you put like negative 0.8, negative 1.0, again, those are fine. You want to be somewhere in between those. Let's take a look at question 2. According to table 1, interpolate the freezing point of a solution with 4 grams of KCl. How would you answer question 2? Well, sorry, first off, what'd you get?
I got negative 3.55 degrees Celsius.
Nice, negative 3.55 degrees Celsius.
And I did that down to table 2. And I looked between 3 and 5 grams of KCl, which the between that is 4 grams. And then I just added 4.30 and negative 2.8. And then divided that by 2, and then I got 3.65 negative.
Excellent. So that was a real specific way, and that's the real scientific way to do it, is to add them up and divide by 2. All right, remember, we do need to start getting comfortable trying to pick out middle numbers maybe without doing the division, because it could save us a good 30 seconds to a minute worth of just math on the paper. That maybe could be another question for us. But yeah, this is exactly how you want to do the answer. All right, you find the average or the middle number between the 2. All right, let's take a look at question 3. Do you have a volunteer to read question 3 for us? Yeah, thank you.
According to figure 1 interpolate, the boiling point of a solution with 7.5 grams of NaCl added to 15 milligrams of H2O. We got 102 degrees Celsius.
I give you 102.
Well, we used the hint, the first hint, for number 3, that it said 5 grams of NaCl had 101 degrees Celsius as the boiling point, and for 10 grams of NaCl, it reached 103 degrees Celsius. So we added those up. We got 204, and divided that by 2, and we got 102 degrees Celsius.
Excellent. So looking for that midpoint, what's between 101 and what's between 103? Well, that would be 102. All right, now how do we get these numbers? Just to make sure we're aware is that we're looking at the one with 5 grams NaCl, which is the dashed line, and the one with 10 grams NaCl, that's the dotted line. So we're looking for where they flatten out, because that tells us the boiling point. So the dashed line flattens out right about there, and the dotted line flattens out right about there. So what would be between the green line and the blue line? Well, that's about 100. All right, we're now moving on to question 4. Using table 2, predict the mass of NaCl required to change the freezing point of a 50 milliliter solution of water to negative 4.7 degrees Celsius. All right.
The first thing I looked at was table 1, because it says mass of NaCl. And then I need to find its freezing point, and it gave me negative 4.7 Celsius. So that's between negative 3.63 and then negative 5.77 Celsius. And since I'm trying to find the mass, I took my line and went to the next column. And then in between 3.0 and 5.0 is 4.0. And that's my answer.
Perfect. Excellent. Outstanding. All right, if you feel like you got through these 4 questions and you can understand this sort of basic version of the problem with some hints, you are ready to move on to the next set. 5, 6, 7, and even get to 8. Once you are done with 5, 6, 7, and 8, you want to press play on the video again so that we can go through the answers together. But right now, you should press pause and work on these 4 questions. And again, as soon as you're ready to check the answers, press play. If you are pressing play at this point, then you can get into questions 5, 6, 7, and 8 and are ready to go through the answers. So let's get started with question 5. We have a volunteer to go through question 5 for us. Thank you, sir.
So according to table 1, interpolate the freezing point of a solution with 7.5% NaCl. So go to table 1, go to percent.
Yeah, because in these, you're always wanting to think about what are they giving me and what am I looking for. In this case, they're giving you a percent and they're asking you for a freezing point. So you're going to 7.5%. Where would that be?
Right there. No, over.
Ah,
Percent.
nice. And this is the biggest trap that people fall for. If they look at this column, they see 7.5. This isn't our percents. This is grams. So you want to make sure you're going to 7.5%, which is in between which two numbers?
6.
Right. So 7.5 would be between 6 and 9. You trace this over. What do you get?
So I added those, negative 6.63, negative 5.77, divided by 2, we get negative 4.7.
Nice. And the trick here to look at it too is negative 3.63. That's super close to negative 3.6. This one's negative 5.7. So it's probably going to be somewhere between. The 4 is going to be right in between them, negative 4.65. All right. Question 6. We have a volunteer to do question 6 for us. All right. Read the question for us.
According to table 3, interpolate the freezing point of a solution with 2.25 grams CaCl.
Excellent. So what are we looking for in this case?
The freezing point.
Freezing points. And what are we given in this case?
We're given 2.25 grams CaCl.
Nice. All right. So we're down here at table 3. All right. We're given grams. Where would 2.25 grams of CaCl2 be?
In the third column,
Good. In the third column, we're looking at grams.
between 1.5 and 3.1.
Nice. Because that's where 2.25 would be. It would be between 1.5 and 3. Trace it over to our freezing points. What do you get?
I got 2 point negative 2.7.
Yeah, negative 2.25 degrees Celsius. Nice work, sir. All right. And last but not least, let's get to 7 and 8. Volunteer for 7. Thank you, sir.
First, I went to, because I go to table 2. Using table 2 to predict the mass of the KIC required to change the freezing point of 50 milliliter solution of H2O to negative 3.5.
All right. Now, don't get tripped up here with this whole 50 milliliter solution of water. Remember, every experiment is using 50 milliliters of water. So that's just thrown in there as extra information we don't actually need. All right. So in this case, what are we looking for?
First, I went to table 2.
Good.
And in the question says I'm looking for the mass.
Good. You're predicting the mass in this case, and you're given the what?
The freezing point.
Nice. The freezing point, which is negative 3.5 degrees Celsius.
Then I look online. Well, I look, see if there's on the freezing point, see if I see 3.5.
Negative 3.5. Yep.
And I see it's not there. But I also see that there's the mass of 3 has 2.8 and mass of 5 has 4.3. So
Nice.
3.5 has 15 mass, so it would be between 3 and 5, which is 4.
Nice. Perfect. Between these two numbers, you get between these two numbers, and that's how you get your answer. Nice work, which is 4 grams. All right, so let's take a look at question 8 then. Question 8 says, according to figure 1, interpolate the boiling point of 50 milliliters of water, 2.5 grams of NaCl added. This is another situation where reading a question, you can immediately cross off this whole 50 milliliters of water thing because it doesn't matter. Every single one of the experiments is run with 50 milliliters of water, so don't let the data kind of get confused because the question is changed. So we're looking to interpolate the boiling point, so we need to look at this figure, the boiling points, of 2.5 grams of NaCl. In order to do this, we have to remember, we're looking for the number that is in between. All right? We're looking for where can we find 2.5? And this is why we said at the very beginning what we have to remember is that this H2O, the solid line, is actually H2O plus 0 grams NaCl. Because remember, they didn't add anything to this, it's just pure water. But you can imagine in your head that it would be plus 0 grams NaCl. So then if we're looking for where we would find 2.5 grams, 2.5 is between which two numbers? Well, it's between 0 and 5. We find 2.5. So if we take a look at our line then, what we're looking for is a boiling point that's in between our 0 line and in between our 5 line. Our 0 line boiling point is right here. Our 5 line boiling point is this dash line right here. So it's sort of in between 100 and that 101. So then what number would be between 100 and 101? That would be 100.5. All right, at this point, if you feel like you've answered question 8 well, you understand all the topics, you want to press pause. You want to press play again after you've answered questions 9, 10, 11, and 12. Now, these are going to already start to get a little bit trickier as questions. Right? The other ones were kind of like right there interpolation questions. These are asking you to interpolate to do a little bit more thinking in the process. All right? When you've answered questions 9, 10, 11, and 12, or if you feel like you're stuck, move on to another one. When you're finished with all 4 of them, press play and go through the answers. If you are pressing play at this point, that means you've answered questions 9, 10, 11, and 12 and are ready to go through the answers. So the first thing we need to do is take a look at question 9. Which would have a colder freezing point? 6 grams of NaCl in 50 milliliters of water, or 6 grams of KCl in 50 milliliters. Again, we can remember that this 50 milliliters thing is really just there as excess wording that you don't really need, so we can always cross it out. So in the end, what we're looking for is freezing points. We're trying to figure out which of these two situations would have a colder freezing point. Remember, to have a colder freezing point, it's going to be more negative. The more negative the temperature is, the colder the temperature. So if we look then, the first one we need to look for is 6 grams of NaCl. 6 grams of NaCl would be somewhere between 5 and 7.5 grams right here. This would amount to a freezing point that's somewhere around negative 5.5 degrees Celsius. All right, now if we look for 6 grams of KCl, 6 grams of KCl again would be between these two. All right, now what you'll notice is that this is negative 4.3 and negative 6.4. So in this case, this number would be much lower. All right, the halfway point, and it would be much closer to like negative 5 than it would be to negative 5.5. All right, now in order to do this, you really have to start to look at the difference between these two. And again, it's sort of hard to internalize it and do the math right away. You don't necessarily want to spend a ton of time doing division. What you'll notice is, like, for our example that we had over here, the two numbers you're looking for are 5.77 to 9.03. And you're looking somewhere closer to the, because if we looked at 6 grams, 6 is a little closer to 5 grams. So you're a little bit closer to this side than the other side. Our other range was between negative 4.3 and negative 6.4. All right, so the range is these ranges. All right, and what you'll see is that this range is significantly lower, or significantly warmer, I should say, because it's less negative than this range. And that's why this range ends up being much colder than this range does. And that's how you can tell that 6 grams of NaCl would have a colder freezing point than 6 grams of KCl. Let's take a look at the next one. Which would have a warmer freezing point? Now this is asking the opposite question. Now we're looking for a number that's less negative. We're looking for something warmer. We're still looking for a freezing point, and our two options are 11% KCl or 11% CaCl2. If we look at 11% KCl, 11% KCl would be actually a little bit closer to 9 than 13, but it would be somewhere in between those two numbers. Again, but closer to the 9 number than the 13. We would trace that over, and what we find is actually it's one of the same ranges we were looking at before. The other option is to take a look at 11% CaCl2. Again, closer to 9 than 13, but between those two numbers, all right, where would it fall? In this case, if we look at our two ranges, again, we're looking at the same range for the first one, negative 4.3 to negative 6.4. Our second range this time is between negative 5.04 and negative 8.72. You'll notice that the second range is a lot colder than the first range. It starts at a colder temperature and it ends at a colder temperature. So what this means then is that this one is going to be much colder than this one is. And now we have to look back at the question. Are we looking for the colder one or the warmer one? We're looking for the warmer one, which means that it's got to be the KCl one, not the CaCl2. So our answer here should be the 11% KCl. All right, the next one is we move on to number 11. Which solution would have more solid dissolved? A solution of NaCl in water with a freezing point of negative 5.5 degrees Celsius, or a solution of CaCl2 in water with a freezing point of negative 5.5 degrees Celsius. In this case, instead of looking for freezing point this time, we're looking for which one would have more solid dissolvent. In order to do this kind of question, we have to realize that more solid dissolved would mean that we're looking for more mass, because mass is the amount of solid that we're dissolving inside. So in this case, we're looking for more solid dissolved, which we know is mass, and we're given the freezing points, negative 5.5 NaCl and negative 5.5 CaCl2. So as we look for these freezing points, the first one we'll look for is the NaCl, because it comes first. Negative 5.5 would be just before this one right here. So between negative 6.3 and 5.77, which you'll notice would be really close, much closer to that negative 5.71 than the negative 6.3. Our other option is to look at the CaCl2, which is down here, and to look for negative 5.5. And what we'll notice, if we trace this over, is that this one would be between 5 and 7.5, whereas this one would be between 3 and 5. You don't even have to do the math interpolation here to see that this one down here, the range is already higher. So we know that you have to add more there than you would there to get to the same temperature. So which solution would have more solid dissolved in it? Well, that would be the CaCl2, because with this number here, it's significantly larger. All right, so that would be CaCl2. And again, these can be tricky because you're actually doing probably 3 or 4 things to try to determine the answer. All right. Now, possibly the trickiest question on here, if you could only use 4 grams of either NaCl, KCl, or CaCl2, and you wanted to decrease the freezing point of water as much as possible, what would you use? Now, this is also the most practical question on here, because essentially what you're looking for is like if you were going to pour salt on the ice in the front of your house, which one of these would be the best ones to use? NaCl, KCl, or CaCl2? So the lower you could drop the freezing point of that water on the ground, the less ice you would have in front of your house. So you only get 4 grams, so you want to use the same amount. So in this case, we're actually just going to clear this to make it a little bit easier to read. All right, so we know we're only using 4 grams, but we have all 3 options. And we want to decrease the freezing point. We want it to be as cold as possible. Which one would we use? Well, if we look for 4 grams would be here, here, right here. Always between the 3 and the 6, closer to the 3 side. In this case, between 3 and 6, we get a range that's somewhere between negative 1.85 and negative 3.63. In this case, we get a range that's somewhere between negative 1.48 and negative 2.8. This last case, we get a number that's somewhere between negative 1.47 and negative 2.93. And again, we don't necessarily have to find the middle number, we're just looking at how cold the ranges are. You'll notice that the range for the first one is always colder than any of the other ones. Because even at the start, negative 1.85 is colder than our other two options. And the end, negative 3.63 is colder than the end options of either two. Which means the one to get the coldest temperature in the end would be NaC. If you need to rewind this explanation and listen to it again, I highly encourage it. This is by far the trickiest question on it. If you feel like you're ready to go on to the last two multiple choice questions, which are questions 15 and 17, you should pause this now and work on it. If you need to rewind, take a look at the explanation for any of 9, 10, 11, or 12 again, you should do that now. Either way, you should continue working just to get the last two questions done. You should pause now if you're going to work on 15 and 17 and wait for the answers later. All right, we're going to continue recording for the last two questions right now. These are questions 15 and 17. You should only be pressing play now if you've already answered these two. We're going to start with question 15. If in experiment 3, a chemist had measured the freezing point of solution 11, the value would most likely be closest to. So again, we're looking for freezing point here. We're also looking at solution 11, which is a weird one. You'll see that solution 11, here's our solution numbers. Solution 11 actually doesn't exist. All right, so what they're saying is what would happen if you were to measure solution 11. What do you think that you would get by measuring solution 11? So we have to kind of look at what the trend is for this one. We see that solution, if we start like solution 7 was at negative 1, 8 goes to about negative 3. This one goes up to negative 4.3. By the time we're at solution 10, we're at negative 6.45. So a couple things we need to see. This number is already increasing, so we can already get rid of 0, because 0 would actually be the temperature too low. Of the options we're left with, the most reasonable one to go up to the next route would probably be negative 10. You wouldn't expect to get all the way down to negative 14 by the time we're here, so you can cross off negative 14. You can also definitely cross off negative 17. You never get down that low. So the answer that we're looking for here is about negative 10 degrees Celsius. For 17, based on the results of experiment 3, a 7.5% solution of CaCl2 would have a freezing point of, and again, this problem is going to seem really easy compared to some of the tricky ones that we were doing before. We're first looking for CaCl2, which is in this table down here. All right, we're looking for 7.5%, that would be between 6 and 9. Trace it over, we know our freezing point will be somewhere between negative 2.93 and negative 5.04. Now again, this is exactly the kind of question we talked about at the beginning. They give you one of the ends of the ranges. They also give you the other end of the range. And you have to see that it couldn't be either of those, because you want to look in the middle. The number in the middle would be choice B, negative 4.01. Again, if you feel like you got these last two questions, then you are ready to go to take the quiz. If not, rewind to whatever point in the video you need to go back to and watch it. Especially the questions 9 through 12 are very important to focus on. Those are questions that are very similar to ones that you might see in a quiz. So if you need to go back and take a look at the explanations of those, I highly encourage you. If you're ready to take the quiz, good luck.